со научниците во светот, позиционирани на респектирани универзитети и истражувачки центри, кои се родом од Македонија, и нив ги мреживме и ги практично вклопивме во академската заедница на нашиот универзитет, UKIM. Во овој момент, практично таа идеја стартуваше од неколку имиња. Главен протагонист на идејата е професор доктор Никола Стиков, кој е професор на Техничкиот универзитет во Монтреал, во Канада, кој заедно со неколку негови колеги во времето на короната направија една заедница на македонските научници во светот, која се вика iesta и која во моментот брои околу 350-400 имиња. Негов прв соработник во тој процес беше токму Кирил Gashteovski, денешниот предавач. Таа идеја се поклопи со нашиот интерес да стапиме во контакт со македонската научна диаспора, да ни помогне во интернационализацијата и подобрувањето на видливоста на нашиот универзитет во светски рамки. И во тој контекст, првите 4 имиња имавме интензивни контакти со нив, 4 врвни научници македонци во светот, со нив го формиравме ЦЕНИС. Морам да ги кажам нивните имиња, бидејќи сум исклучително благодарна на нивниот придонес и целиот напор кој го прават овие години и кои практично со разни задачи си поставуваат своји наредни цели во периодот кој престои. Значи Никола Стиков, Јадранка Стојановска, професор на Универзитетот во Њујорк, инаку во областа на медицината, професорка Розита Димитрова, професор на Универзитетот во Берлин, хуманист, значи антрополог, и професор Петар Поповски, електроинженер, професор на Универзитет во Данска, а сега и професор Панче Наумов, професор на Универзитетот во Њујорк, со седиште во Дубај. Тие се сталните, значи постојаните членови, оснивачите на ЦЕНИС, и по функција тамо се двајцата проректори, проректор за наука и проректор за меѓународна соработка и еден представник на МАНУ. Тоа е практично телото кое е движечката сила на овој центар ЦЕНИС. Во него вмрежуваме, како што реков, научници од светот. До овој момент има 15 члена, а таа активност е постојана, континуирана и очекуваме оваа година таа бројка да се зголеми. Нивната помош е во контекст, тие добиваат Research Fellow на UKIM и право да ја користат афилијацијата на UKIM покрај својата матична афилијација, публикуваат со наша втора афилијација, со што го зголемуваат нашиот research input, research output како универзитет, зашто ние се залагаме, тоа е едната голема работа која ни е потребна за видливоста и интернационализацијата. Потоа се иницираат заеднички проекти и овозможуваат престој, значи соработка нивна, лоцираме истражувачки јадра на нашиот универзитет во областа во која работат научниците во светот и правиме таков мечинг, поврзување, и од тие врски произлегуваат престои за можност за напредување на младите наши соработници, докторантите, асистентите, помладите професори, звања во доценти, во редни професори, да се вмрежат со универзитетите и институциите во светот. Значи, сега јас се извинувам, можеби 2-3 минути одземав, меѓутоа ви благодарам на сите што дојдовте и што пројавивте интерес, главно заради темата на предавањето на денешниот предавач, меѓутоа должна сум да ве запознаам со идејата на која интензивно работи нашиот универзитет. Оваа идеја започна заедно со проректорот во претходниот мандат, професор доктор Ордан Чукалиев, и тој е сега раководител на центарот ЦЕНИС. a pokraj него како секретар кој практично е задолжен за комуникацијата со сите луѓе во странство и за практично овозможување да непречено административно се реализираат сите тие активности. Тука е Катерина Климовска, која е дел од Оделението за наука, истражување и развој во ректоратот на Универзитетот Свети Кирил и Методи. Значи, директно се тие две имиња кои се одговорни за операционализација на активностите на центарот овде кај нас. А како што кажав јас по функција и мојот колега професор Александар Скепаровски како проректор за меѓународна соработка, ние сме сега во тој борд, во тоа тело. Јас тука би запрела во однос на прикажување, представување на големата слика. Би сакала неколку збора за нашиот денешен предавач Кирил Gashteovski, значи тој е исто член на нашиот ЦЕНИС, зашто сме исклучително задоволни и благодарни. Член е од минатото лето, а веќе има неколку публикации со афилијација на UKIM и е вмрежен со наши истражувачи, главно истражувачки центри тука, професори на финки. Бидејќи работи во област која природно припаѓа на финки, меѓутоа има своја апликација во различни науки, научни и истражувачки подрачја. Професорот Кирил Gashteovski има докторирано во Германија и сега работи како senior researcher во НЕЦ лабораториите во Европа. Значи, на висока позиција на која има право да практично сам одговара, односно има право да допишува и други дополнителни афилијации кои ги стекнал со неговите резултати во истражувањето и неговото реноме. А гледаме дека е исклучително млад, зашто јас навистина му честитам. И практично тука јас Кирил би запрела областа со која вие се занимавате, data science, machine learning и така натака. Сите тие елементи ќе ги испрезентирате вие. Јас сум исто исклучително заинтересирана да слушнам детали од вашето истражување, така да ќе бидам членот на публика. Ви го предавам. Повелете.
Hvala mnogo. Hvala mnogo, Валентина, за introduction, за мојот повед. Сега јас би продолжил да презентирам на англиски, бидејќи полесно презентирам на англиски. Okay, so today's talk is going to be about the research that we're doing in NEC Labs Europe in Heidelberg. And the title of this talk is Tell Me the Facts and I Learn, Methods for Factual Information Consumption from Large Textual Corpora. So the talk is really going to embody the vision of NEC about AI and in particular for natural language processing, but also the research that we have been doing in our lab. So just before we dive into the topic, I'm just going to do a little bit of shameless advertisement of our group. So just to give you a sense of who we are and what we do. So we have, our group has more than 20 top-tier publications that are published on conferences like AAAI, ACL, NeurIPS, and so forth. Occasionally we get lucky and we win awards, like the Outstanding Paper Award we won in 2019 about graph-based AI. And regarding the scientific branding, we are sponsoring top-tier conferences sometimes. For instance, we sponsored TMNLP last year in Singapore and ACL as well. And some of our people, our group leader, Caroline, for instance, was a senior area chair for the ACL 2023 conference. And so we do tend to publish our research. You can really read our papers; they're online, available. So we try to publish everything that we do research-wise. Okay, and one other thing that's perhaps relevant for here is that we really love universities. So we collaborate with universities pretty frequently. This is just a glimpse of the universities that we have collaborated with. You can see we have collaborations all over the world, from the University of Würzburg in Germany, Carnegie Mellon University in the USA, University of South California in USA as well, Tokyo Tech in Japan, KU Leuven in Belgium, VU Amsterdam in Netherlands, University of Copenhagen in Denmark, and University of Zagreb in Croatia. So if you want to do research and you want to kind of also collaborate with an industrial lab, I do encourage you to approach me via email, LinkedIn, or whatever. And then if we find touching points, I'm sure that we can make some collaboration happen as well. Okay, so now that you know who we are, let's talk about the vision that we have and for artificial intelligence in general. So our vision is to create understandable and supportive AI systems that extend human capabilities. And this goes in line with NEC's 2030 vision, which is about expansion of collaboration between AI and people. So we don't believe in the notion that AI will replace humans. We believe in the notion that AI will enhance humans. So with our work, we're really trying to support humans to be better at what they're doing and to be more productive and to be more efficient. So that being said, we, at least our group and the research that I'm doing, we're working with natural language text data, which is unstructured and inaccessible. So if you think about it, it's like having this big pile of mess that you see on the left side, and what we're trying to do is make it somehow machine understandable and structured, so that you can put it in the database, you can query it, you can make it really useful. And so the question that we really try to answer is, can we make this knowledge in the text data more accessible? And so to do this, we really need to do cross-document information consumption. What does this mean? So imagine that you have a lot of documents somewhere. This can be business data, this can be academic data, newspapers, anything you can think of that's written in natural language text data. And keep in mind that according to many business reports, most of the data that exists today in the world is in unstructured format. So it's not neatly packed in tables, as you see in many database courses maybe, but that's rarely the case. In most cases, the data is actually spread into unstructured information. And so if you have some user that really wants to use this data, the user cannot really go directly to all of these hundreds or thousands of documents, or millions even, and just get what the user needs, but we really need something better. And this problem is like getting information off the internet or of the textual data is like taking a drink from a fire hydrant. That's how it really is. You have huge amounts of textual data, and you can't really access the knowledge directly. What if we use a retriever? The most famous retriever would be the Google search engine that everybody's using, or Bing, or whatever. But this is still overwhelming. So retrieving directly from documents is really still overwhelming, because the retriever might return whole documents as answers or links, but not the targeted information that the user really wants. So that's why we can't really rely on retrievers if we really want to make the data accessible like this. What about large language models? I mean, many of you have played with ChatGPT here. You know all the things that you can do with it. Still, you can't really use them because the prompt size is limited. So you can't really fit a large amount of documents in a prompt. You can't throw 100,000 documents to ChatGPT and ask questions about it. That's not going to happen. And so again, therefore, we need something else that we can make this problem more approachable. And so to do that, we turn to the problem of fact extraction. which in the literature is also known as open information extraction. So what does this mean? This means that we're trying to extract facts from natural language text. And as an example, consider this sentence. Suppose you have a sentence like this: Michael Jordan, who played for the Chicago Bulls, was born in Brooklyn. Then with fact extraction frameworks, we will try to structure the data into triples. And so you have one piece of information is from this sentence that can be extracted is that Michael Jordan was born in Brooklyn. And the other one is that Michael Jordan played for Chicago Bulls. Now you can see now you have a structure. Now you have a subject, you have a relation, and you have an object. And you can really work with this machine-wise better. Just put it in a database. You can construct large knowledge graphs from this, and therefore you can really query this data, and instead of just having a huge amount of textual data, which is hard to query. And so when you run such fact extraction models on large amounts of data, say you run it on the entire internet, or you run it on the English Wikipedia only, this will automatically create huge repositories of such structured facts as I showed you. And so these are going to be cross-document facts, because the fact extraction does not care about the entire document. It really cares about this atomic unit. It really cares just about the fact itself, structured as a subject, relation, and object, which means that whatever you extract is cross-document, so it goes beyond one document that you have. And this allows the user to explore the facts from the entire corpus, from the entire collection of documents. So let me show you an example for this. Suppose we have some fact retrieval framework like this. And then you want to search for an entity. In this case, we want to know something about Carl Benz. This is an actual example. We processed the entire English Wikipedia, we put it in a database, and this is what we got. And then you will get some search results like this. So Carl Benz is an inventor. I don't know if you can read it from there, but what it says here: Carl Benz, B, inventor. Carl Benz is automated pioneer. Carl Benz is German engineer, was inventor of gasoline powered engine, and so forth. So you already know who Carl Benz is without reading a whole document about it, like a Wikipedia article, which takes more time to actually read instead of having it structured like this. And then on the right side here, you have frequency of the fact. This tells you how many times this fact appeared on your entire collection of documents. So let's say we want to know about Carl Benz being an inventor, which appeared 5 times in our example. In the entire Wikipedia, Carl Benz that was an inventor disappeared in 5 times. So if you click on that, then you will get all the Carl Benz being an inventor facts and where they came from. So they came from the Wikipedia article about Karlsruhe, about Benz, about Elwood Hines, and so forth. Then if you even want to explore further, you can click on the other fact, on one of these facts, say from Karlsruhe, and then you will get something like this, where you find the exact place in text where the information came from. So you already know if the fact is something you are going to trust or not. And so here it's highlighted where it came. So it came from this part of the sentence that Carl Benz was an inventor from Karlsruhe, and this is where this information came. Okay, so how do we get from there to here, actually, from higher corpus of textual data like the entire English Wikipedia to something like this, where you can actually basically just explore in a structured manner? Well, to do that, we have a lot of challenges that we need to solve first. The first challenge is data annotation. So if you want to train a machine learning algorithm or even evaluate it, you really need to have annotated data that was done by humans. And then with this, you train your model. And then with this, you evaluate your model as well, so that you know whatever is it that you trained actually works. To do this, we worked on Annie, which was work that we published on ACL 2022, with the lead author being Nicholas Friedrich from the University of Mannheim. And what we did here is we posed the question how to efficiently annotate training and evaluation data for these factor checker problems. And so the need here is to create training and testing data for new domains, but also languages, because most of the work out there is on English, but there are other languages that people need to use these technologies for. And so we kept this in mind, and we created the annotation framework that is also going to be able to support different languages. So we did experiments here on English, Chinese, German, Arabic, and there was one other language that I forgot now. It was, I think, one of these regional languages in Spain. I don't remember which one was it, to be honest. Nevertheless, we covered a wide range of languages. Then what we also observed is that the current training data for these sort of programs is actually created automatically. They were using some sort of distance supervision assumptions, which really at the end gives you data that is really noisy, has a lot of mistakes in it, a lot of errors. And so this results, of course, in training algorithms that don't work really well because they're trained on bad data. And so our solution is Annie, an annotation platform for such fact extraction models. And with Annie, we accelerated the process of annotating such extractions. So basically, you have the user interface with the annotator when it starts using our framework. The annotator is already going to see some highlights, are kind of like hints helping the annotator. This word might be a relation. This word might be a subject, an object, an entity. And so this is kind of the nudge that we're giving to the user. And this results in really faster annotation. And once we have that, the user really just clicks and drags and drops. And this is how the annotation goes. Then you can see you have an input sentence, and then at the end is the answer. Subject, relation, object, triples. This format. Okay, so now that we solved the challenge about annotation, there's another challenge, which is the evaluation challenge. So how do we know if we built a model for fact extraction that is actually working? And so for this, we published the paper Benchy on ACL 2022, where I was the lead author here. And here the question that we asked was how to reliably estimate the performance of such fact extraction systems. It's not like we invented something. The fact extraction systems, they exist here for since 2007, so it's been quite a lot of work on this, almost 17 years. But the problem was that we noticed that there are not really good automated ways of evaluating, and so therefore we turned to creating this, because we found that current benchmarks where we're actually testing these models, they overestimate the performance. They're too optimistic, and also they're monolingual. They work only on English. They don't work on other languages. So to tackle this, we proposed Benchy, which is a benchmark that is capable of evaluating such fact extraction systems more reliably and also in multiple languages. So just to show you an example of this, the blue bar you see here is the previous benchmark that was considered to be the state of the art. Now, we ran some experiments and we found for model 1 that the previous benchmark gives 61% of F1 score. So this seemed pretty high considering the experience we've had with these models. And once we worked on Benchy and made the annotation with Annie and packed everything together, we found that Benchy actually tells you, well, the F1 score is not 61, it's 21. So you can see that the previous benchmark was so unreliable, it really would give you the impression that the model is 3 times as good as it actually is. And we noticed this on many other models. So it was not just one model that had this behavior on these benchmarks, but all the models, without exceptions, that we tested, we found that the previous benchmarks are really overestimating the performance. These fact extraction systems are not as good as people thought they were. So once we did that with the evaluation, now that we have the annotation, we have the evaluation, now we are actually ready to build the fact extraction model. And to do this, we proposed a multilingual fact extraction model. This was work that we published on ACL 2022 with Bhushan Kotnis as lead author here. And what we did here, we proposed MILI, which is an iterative approach that is conditioned on extracting different parts of the fact. What does this really mean? Suppose you have this sentence, right? You have Barack Obama became the US president in the year of 2000. Now, with MILI, you will give something as an input. For instance, you can give a predicate candidate, and this could be a verb, right? So you find the verb maybe in the sentence, and you say to MILI, what is the probability that the predicate, that the subject is Barack Obama, given that the predicate is became? And then MILI is going to give you some probability, then it will iterate, and then it will ask again, maybe, what is the probability of the object being US president, given that the predicate is became and the subject is Barack Obama, and then it iterates again until it extracts the fact that Barack Obama became US president in the year 2000. And so when we proposed this, we also integrated MILI with existing systems, because you can give these candidates with other fact extraction systems that maybe are good in extracting some parts of the facts, like the predicates or the subjects. This is something we have noticed in the past. And this other part, the object, is something that is usually more difficult to do because of also because of the structure of the English language, because you might have conjunctions, you might have all sorts of complexities on sentence that makes it difficult for a fact extraction system to extract the object. But with MILI, we kind of mitigate this by providing the other slots from the fact from other more reliable systems that we know work good for this. And then if you want, you can integrate MILI with these existing systems, but it also extracts facts from multiple languages. So it doesn't really focus only on English, it focuses on other languages as well. What we found in our paper is that MILI was the best performing neural system on the benchmark that I showed before. And so with this, we have the challenge of fact extractions already tackled. So to maybe just refresh here, we have a big pile of documents you want to get to the user, where the user really explores structured way of information from the unstructured text documents. We have the first challenge of annotation, the second of evaluation. The third challenge is about the fact extraction model that uses the annotation and the evaluation to create a database of facts, right? And now you would think, okay, we have the database of facts, we're ready to go. Well, it seems like no, it actually is more complex than that. So we found there's another challenge. We have a fourth challenge now, once we have the facts stored like that. The problem here is that we have multiple representations that have the same meaning. So what does this mean? Suppose we have again this fact about Michael Jordan was born in Brooklyn. We all know who Michael Jordan is, I hope, or maybe I'm too old to know who he is. But as you might know, Michael Jordan is referred to in the media with different names. So he's Air Jordan, or Michael Jeffrey Jordan, or he's Ernest. Now, if you really are having text that you're querying in your database, if you're looking just for Michael Jordan, it's not going to give you Air Jordan or his Ernest because these entirely different words, right? So what do we do here? Here we see that this is a clustering problem, actually. So how do we cluster such equivalent terms, Air Jordan, Michael Jeffrey Jordan, his Ernest, into a single semantic group? What does this mean? Well, this means that all of these strings, all of these textual representations about Michael Jordan, they should all map to the same thing, whatever that means, right? And so when you query it, the AI should know what you're looking for, even if you're looking for his Ernest, right? It should give you results for Michael Jordan. So we really need to put these together. To tackle this, we turn to the clustering problem, which basically is on the left side, you have some data points completely unlabeled. And you have to put them into some structure that makes some sense. Now, this is very, very ambiguous and difficult because what does it really mean to have a right group of data if you don't have labels? And this means that the problem is actually context dependent. It really depends from the context of the text you have. So all of these clusters might look right, even though they're different. But it really depends on what context are you using them. And so, for instance, Michael Jordan in one text could mean the basketball player, but it could also mean the machine learning professor in Berkeley, whose name is also Michael Jordan. And so this is context dependent, right? So this is what we mean by this. And to tackle this, we work with Carnegie Mellon University with Vijay Vishwanathan as a lead author here. And this paper was accepted at the Tackle Journal, which is going to appear this month, some days from now, probably. And basically what we did here is we actually turned to semi-supervised clustering, which incorporates human feedback, precisely because it's context dependent. Humans should really tell what is a cluster, right? We do it out of the blue, most likely, especially for language, it's not going to work. And so to do this, we turn to semi-supervised clustering. This means you have this unlabeled data, you give it to a user, and then the user says, okay, this data point belongs to this group, and this point belongs to that group, this data point belongs to that group, but the human does not annotate everything, right? So it annotates just a smaller sample of the data, and then you give it to a clustering algorithm to figure it out, the rest, right? However, there's a problem here. It turns out in many clustering algorithms, you actually have to annotate a lot of data in order to get the clustering algorithm to work, to the semi-supervised clustering algorithm to work. And so even this is something that poses realistic problems when you use these algorithms, because you need to hire a lot of people to annotate. It takes a lot of time. It takes a lot of resources. So it's not something that we necessarily want to do. So we want to kind of solve this problem and use large language models to do this. So with our approach, we use the large language models to guide the cluster. So what does this mean is, as you can see now, the user is annotating very few data points, much less than in the previous standard semi-supervised clustering. And then we give this to a large language model, and then we say, hey, here's some small data points, please annotate the rest. And then the large language models are doing this, and then we feed this to clustering algorithms, and it turns out that this works really well. And our method, we actually applied it on 3 stages of the clustering process. So before the clustering, we use the large language model to enrich document representation. During clustering, we use the large language models to add some constraints to the clustering, saying something like, this data point must not be in this group period. Right? So if you have something like, I don't know, Napoleon Bonaparte, there's a strict rule. He's not a basketball player, so just don't put it there, right? That's a strict rule there. And then after clustering, to use the large language models to correct low confidence clustering assignments, because the algorithm might give you some, here's some clustering assignment, but this one has a low probability, and then the large language model double checks this and says, okay, this is good to go, or no, this should be another cluster. With this, we observed improvements on these entity clustering problems. So, about his Ernest, Michael Jordan, everything, but also on other clustering tasks. So we observed that this works also on tweet clustering and unsupervised intent detections. We did experiments on these problems as well. It turns out it works there as well. All right, so now that we clustered these entities that have different representations but have the same meaning, maybe we're ready to go. Well, it turns out we're not. We have one additional challenge, which is linking these fact elements. What does this mean? Well, this is the problem of resolving ambiguities. And this is because elements in such extracted textual facts are ambiguous, which I already kind of hinted before. Let's go with the same example. So Michael Jordan was born in Brooklyn. At least something you will remember from this talk is that Michael Jordan was born in Brooklyn. So who's Michael Jordan now? Are we talking about the basketball player or the computer science professor? So which one is it? For Brooklyn, is it the borough in New York? Or is it this small town in New Zealand, which is also called Brooklyn? So which one is it? Yeah. And even this was born in, what does that mean? This is just a string that does not really have a precise meaning. So what do we do with this? And so to tackle this problem, we published a paper last year on EMNLP with Gorjan Radevski as a lead author, who was actually a student at this university, but is now a PhD student in KU Leuven in Belgium. And so with him, we worked on this problem, and with other colleagues, of course, and we turned to knowledge graphs. So what are knowledge graphs? These are structured graph databases that contain facts with unambiguous elements. And so this weird thing you see here, these are just IDs that are referring to really precise concepts. So the first, the subject refers to Michael Jordan, the basketball player. The second one is signifying a place of birth of a person in some location. It has precise meaning or schema. Brooklyn here refers to the borough of New York City. It's really clear what this fact means in this context. And so with our work here, we wanted to link these textual facts to disambiguate them back to knowledge graphs and say, okay, in this first fact, Michael Jordan played for Chicago Bulls. Michael Jordan refers to the basketball player, doesn't refer to the computer scientist. Played for refers to the relation, meaning member of a sports team in Wikidata, and Chicago Bulls refers to the NBA basketball team, because we found that there are actually multiple Chicago Bulls teams, and not all of them are basketball teams. So even that is not entirely clear. And so we did this with a two-tower machine learning model, which is inspired by image video text retrieval. Basically what this means, it's a pretty simple idea actually. So the two towers is a metaphor having two towers. Tower one has encoding of the textual information into some embedding space, meaning that the textual information becomes a vector. It's just a vector. Second tower is the information from the structured knowledge graph, which we also run through some embedding layer. Then you get a vector as an output again. And so you have two vectors. And now it's just linear algebra. All you do is you're trying to see the textual fact, the embedding space here is really close to the embedding this fact, the embedding space from the knowledge graph. And if they are, that means that it refers to the same concept. So this is the high-level idea of how this works. Okay, now that we have all of these challenges solved, now we can have the factor tree. You can see it's really challenging to get there. It's not just, it's not straightforward at all. And the idea here is to have the right facts across multiple documents at the right time for the user. And this means that the user really gets to choose the facts that the user wants to know from this entire huge amount of textual data. And so our final vision is, because of this, to have understandable and supportive AI systems that extend human capabilities. Again, we don't think that AI will replace people, but it will extend people's capabilities to do research, to do science, to do medicine, to do whatever you think. So consider you have a doctor that has a patient, then doctors are too busy, they have way too many patients, they have also way too many literature to read, to update themselves. And then say there's an incoming patient that the doctor suspects is either Parkinson's or Wilson's disease. And so the doctor might ask the AI, what are the possible symptoms for Parkinson's and Wilson's disease? Because there's just too much text to read. The literature comes out all the time. It's hard to follow. And so the AI would read all the text that exists or is available to it, extract all the real relevant information, maybe represent it somehow in an understandable way to a human. And then you have something like this. So the AI might find facts that KF rings never causes Parkinson's disease, but it's a prerequisite for Wilson. Because also in these diseases, many of the symptoms are really similar. So you need to do differentiable diagnosis to separate the patients from the right diagnosis, lest you do the mistake that you think the patient has some serious disease, you give them the wrong medications, and then that's really, really bad. And so with this, our hope is to have an AI system that will help the medical professional with information like this that would say something like both diseases have similar symptoms, but the KF rings are a key difference. So maybe just look for there. You have maybe additional evidence for this, then kind of guide you through this process. And so with this, we hope that we're on the path to achieve understandable and supportive AI that are going to extend human capabilities. Okay, so this concludes my talk, and if you have some questions or comments, I'll be happy to